Welcome back. Today, our focus of discussion will be explaining the energy displacement graph in simple harmonic motion. Simple harmonic motion is a periodic motion such that the acceleration is proportional to the displacement and is in the opposite direction to the displacement. And we know that a periodic motion is a motion that repeats itself periodically or at a regular interval. Energy is the ability of an object to do work. Okay, so let me just note down some simple points. Simple harmonic motion is a periodic motion, and we say a periodic motion is a type of motion that repeats itself at regular intervals. Okay, and we said the acceleration is proportional to the displacement. And acceleration is in the opposite direction. To the displacement. Okay. We know that energy is the ability to do work. But for simple harmonic motion, the energy we are talking about here is mechanical energy. And mechanical energy is kinetic energy and potential energy. Kinetic energy is the energy that a body possesses because of its motion. And for potential energy, it is the energy that a body possesses by virtue of its position. Okay? So, if we take one of the examples of a body moving in simple harmonic motion, a common example is the simple pendulum. Let's say I have a simple pendulum like this. Okay? We have the string of certain length, L, and this is the bob. Okay? So, this is going to be the equilibrium position of that pendulum. That is, here I have given it a displacement, okay? And at this point, if this is the point I am releasing it, this is the highest displacement. And the highest displacement attained, it is what we call the amplitude. So if I release this simple pendulum, what happens? It will begin to move this way, move this way, move this way. It comes to this point. This point here, it is known as the equilibrium point. It's called the equilibrium point or the equilibrium position. But because it has energy, what will happen is it will continue to move to the other direction until it reaches that same amplitude again, A. That is, until it reaches that maximum displacement. Okay? Let me try to draw that so that it can be in line, roughly. Okay? So let's just try to make this a bit clear. If you have a simple pendulum, and this is where you position it, that is, you are trying to give it some displacement. And when you release it, the maximum distance the pendulum is displaced is called the amplitude. So let me say that I have released it from the amplitude, that is from its maximum displacement. What happens is, for it to move in simple harmonic motion, the motion will be a to and fro motion. So this is how it will be going and coming back, going and coming back, going and coming back. That is called periodic motion. Okay? And the two energies that are related to a body moving in simple harmonic motion, they are mechanical energy, and one of them is kinetic energy and the other is potential energy. Okay, so if you should analyze this body when it is at its amplitude, we can talk about its having a height from the horizontal line. But as it tries to approach the equilibrium position, what happens? If I should analyze the height, it progressively decreases. It goes beyond the equilibrium point to the other side. It starts to increase again. So there is one of the mechanical energies that is related to height. That is potential energy, right? So, which means the potential energy is actually at its highest when the body is given maximum displacement. I repeat that the potential energy of a body moving in simple harmonic motion attains its maximum potential energy at its amplitude. Okay? So because you can see here, the height here and the height here are different. It's higher here. Then as it is coming towards the equilibrium position, it decreases. Then after it passes the equilibrium position going to the other side, it starts to increase here again. So, point to understand here is potential energy is maximum at the amplitude. Okay. So where the potential energy is maximum, wherever you reach maximum, then the kinetic energy at that point will be zero. Just understand that. Okay? So kinetic energy, therefore, is zero at the amplitude. Right? It does make sense. So let's say the body is here at the equilibrium position, then it starts to move towards the amplitude in any direction. Okay? What actually happens is, from the equilibrium position, the speed, or let's say the velocity, decreases progressively. Okay? So if it did not decrease, what would have happened is it would even have passed. It will be continuing to move, okay, away from the equilibrium position. No, but because the kinetic energy decreases progressively from the equilibrium position, then when you reach at its maximum amplitude, the kinetic energy there becomes zero. Okay? Because there, from that point, it begins to turn back. So this tells you that it did not have a velocity there. Okay? The velocity there is zero. Let me repeat myself. At the amplitude, potential energy is maximum, kinetic energy is zero. Okay? So the potential energy is zero at the equilibrium position. Okay? And that is also simple to understand, because if you look at it here, at the equilibrium position, we almost do not have a height as compared to the height that we have at the amplitude. Okay? So, but what about the kinetic energy? Kinetic energy is maximum. Is maximum at the equilibrium position. Okay? So let's say I start to displace the object from the equilibrium position. It moves this way towards the amplitude, and as it reaches the maximum amplitude, what happens? When the body is coming towards the equilibrium position, the speed actually increases, okay? Or the velocity increases. But as it passes towards the other side, it begins to decrease again. That is the case for kinetic energy. So with that, we can conclude that kinetic energy is maximum at the equilibrium point, while at that equilibrium point, the potential energy is zero. So what is important to know is that at any point, okay, at any point of displacement, the total kinetic and potential energy is always conserved, is the same. Okay? So if you add the potential and the kinetic energy together, the total energy will always be the same. Okay? Okay. So with this information, we can move on to discuss the energy displacement graph or curve. Okay? So the energy displacement curve is just to explain the ideas that we have talked about, representing them on a graph or a curve. Okay? We'll have and another line. Let me okay. So we will have energy measured in joules, okay, and we will have displacement x measured in meters. Okay, so but we've said something about the maximum displacement x. That maximum displacement x is given a spatial term. We call that amplitude. So let's call this A. So if this is 0, this is the equilibrium point, and this will be negative A. Okay, so we have energy displacement curve or graph. Okay, energy displacement curve or graph. All right, so here we're going to talk about two energies. Okay, just like the simple pendulum model that I have just drawn earlier and talked about, we are now going to represent that on this velocity on this graph. So okay. Okay, so this is the energy displacement graph, and if you look at it, we have two parabola shaped curves. One of them, the one that looks like an N shape, I call it, is called the kinetic energy. It's showing the kinetic energy. Okay, so if you look at it, it is open downwards. Okay, and the other one is the potential energy, that is U shape. Potential energy. Okay, so with this graph here, we want to explain how the potential and the kinetic energy changes displacement. Okay, now for kinetic energy, if you look at it from the equilibrium position 0 here, from the equilibrium point, okay, kinetic energy is exactly at its maximum here. at the equilibrium position. Okay, at the equilibrium position, kinetic energy is maximum. But if the object is displaced, okay, from its equilibrium position, so as it is moving towards the amplitudes, what happens? You look at it, the energy decreases, okay, progressively. When it is at its amplitude, okay, doesn't matter on both sides. When it is at its amplitude, okay, the energy is zero. Kinetic energy becomes zero at its amplitude. We see that. For potential energy, however, the energy at its equilibrium position is zero here. Okay, as it moves towards the amplitude, look at it. What happens? The potential energy progressively increases. It progressively increases until at the amplitude, so where it is maximum. So this point here, it is called the total energy. Okay, and kinetic energy is represented with the letter K. Potential energy is represented with the letter U. Total energy is represented with the letter E. Okay, so E at any point, the total energy is kinetic energy plus the potential energy. Let's go over this energy displacement graph again. We've said that at the equilibrium point, if you look at it, potential energy is zero, while at that same equilibrium point, kinetic energy is maximum. So kinetic energy has its highest level, or is at its highest. Kinetic energy is at its highest at the equilibrium position or point, while potential energy is at its lowest. So from the equilibrium point, potential energy progressively increases. It increases until at its amplitude where it is maximum. Okay, so potential energy is maximum at the amplitude. But what about kinetic energy? Kinetic energy progressively decreases from the equilibrium point towards the amplitude. From the equilibrium point towards the amplitude, you see that kinetic energy progressively decreases. So when it reaches at the amplitude, kinetic energy becomes zero, okay, while potential energy is maximum. Okay. Now, we do have equations for kinetic energy. Kinetic energy at any point, and at that point we are talking about displacement. Kinetic energy is equals to half m omega squared into a squared minus x squared. Kinetic energy is half the mass of the body in simple harmonic motion, the angular frequency squared into the amplitude squared minus the displacement. Okay, so potential energy is half m omega squared x squared displacement. All right. So we've said that the total energy E is equals to K plus U. So E is equals to, what is K? K is half m omega squared into A squared minus x squared plus, what is U? Is half m omega squared x squared. Okay, so E is equal to, if I should further simplify this, let's try to expand. This will be half m omega squared A squared minus half m omega squared x squared. Okay, then plus half m omega squared x squared. Okay, what I did here is simply to multiply this expression by A squared, then multiply this expression by x squared. That will give me this. And this is already maintained here. So what do we have? If you look at it, minus half x squared plus half x squared will cancel each other. So which means the total energy actually is half m omega squared A squared. So three important energies to note is the total energy, the potential energy is half m omega squared x squared, the kinetic energy is half m omega squared into A squared minus x squared. Okay, so these three formulae are important when solving problems of simple harmonic motion. All right, now let's try to see what we can do with this. We've said the kinetic energy, K, the formula is half m omega squared into A squared minus x squared, right? So when the body is at zero displacement, that is exactly at the equilibrium point, what do we have as the kinetic energy? This will be half m omega squared into A squared minus 0 squared, right? If I should substitute x as 0. So kinetic energy will be half m omega squared A squared. Okay, so that is what? If you look at it, that looks like total energy. Okay, and we are correct. At the equilibrium point, because the potential energy is 0, the total energy is only from kinetic energy. That is correct. Okay, so at the equilibrium point, we do not have potential energy. Potential energy is 0, so the total energy is equal to the maximum kinetic energy. The maximum kinetic energy and the total energy will be equal at the equilibrium point. Okay, so at the amplitude, what do we have? If we have kinetic energy as half m omega squared into A squared minus x squared, but we know that at the amplitude, x and A are equal. Okay, so the maximum displacement x is actually A, right? So if we should say half m omega squared into A squared, what is the displacement? The x will be A, so that will be A squared. So A squared minus A squared, this will be half m omega squared 0, right? 0. At the amplitude, what happens to kinetic energy? Kinetic energy is 0. Okay. So let's talk about the potential energy. The potential energy. At the equilibrium position or point, if I use the potential energy U as half m omega squared x squared, so we know that at the equilibrium point x is what? The displacement is 0. So U is equals to half m omega squared 0 squared. And when you do that, 0 multiplied by any number, U becomes directly 0. The potential energy becomes 0. Okay, let's talk about the amplitude, the potential energy at the amplitude. Okay, again, using the same formula, U is equals to half m omega squared x squared. Okay, U is equals to half m omega squared. So this x, we can change it with what? With a, because we're talking about the amplitude. Maximum displacement is a, so it will be a squared. So U equals to half m omega squared a squared. What does this look similar with? It looks similar to the total energy, okay? And we are right. At the amplitude, if you go back to the graph, at the amplitude, here, this is the amplitude. Kinetic energy is actually 0 here. You can see it. But the potential energy is maximum. And so the total energy is actually given by the potential energy at the amplitude. So, in summary, at the equilibrium point, the total energy is from kinetic energy. It's given by the kinetic energy. But at the amplitude, the total energy is given by the potential energy. Okay, so we also need to know the velocity at any point or the speed. Okay, the velocity. The formula for velocity, V, is equal to omega into the square root of a squared minus x squared. That is, V, the speed, is equal to the angular frequency, the square root of the amplitude squared minus the displacement. So the velocity at any point. And when I talk about at any point, I'm talking about the displacement. Okay, so the velocity at any displacement, the formula for finding V is equal to omega into the square root of a squared minus x squared. So what will be the velocity at the equilibrium point and at the amplitude? Okay, so at the equilibrium point, if you use the same formula, V is equals to omega the square root of a squared minus x squared. So at the equilibrium point, what is x? X is 0, right? So this will be V equals to omega the square root of a squared minus 0 squared. So V equals to omega the square root of a squared minus 0. So there is no need of writing that, okay? 0. So what do we have? V equals to omega square root of a squared. So V is equal to, if you have square root of a squared, this will cancel this. So V is equals to omega a. So velocity. So where do you attain the maximum velocity? Is at the equilibrium. Is at the equilibrium point. Okay, maximum velocity is attained at the equilibrium point. That is where the kinetic energy is even highest, if you can remember. And kinetic energy is proportional to the velocity, right? If you increase the velocity, the kinetic energy will increase, okay? Because you have energy, kinetic energy is half mv squared. So if the velocity increases, or if the kinetic energy increases, the velocity increases. All right. So at amplitude, again, if I should use the same formula, V is equals to omega, the square root of a squared minus x squared. At the amplitude, what is the displacement? The displacement is the same as a, so that will be a squared minus, instead of writing x squared, I would say a, so that will be a squared. So what happens? Omega into a squared minus a squared is 0. So if 0 is multiplied by anything, that will be 0. Okay? So which means at the amplitude, the velocity is actually 0. Okay? At the amplitude, the velocity is 0. So just to give a quick recap, we've talked about simple harmonic motion. We said that it is a periodic motion, and a periodic motion is any motion that repeats itself. We said that the acceleration is proportional to the displacement, which simply means as the acceleration increases, the displacement also increases. And the acceleration is equal to the angular frequency multiplied by the displacement x. So, but we indicate the negative sign there to talk about the acceleration is in the opposite direction to the displacement. Okay? So, we said the energy is the ability to do work, and the energy that we talk about in simple harmonic motion is mechanical energy. And for mechanical energy, there are two. We have kinetic and potential. So potential energy is maximum at the amplitude, while kinetic energy is maximum at the equilibrium point. We talked about the graph, and we've seen how kinetic energy changes from the equilibrium point to the amplitude. It progressively decreases. But from the equilibrium point to the amplitude, the potential energy progressively increases. We talked about the formula for kinetic energy. Okay, is half m omega squared into a squared minus x squared. And the formula for potential energy at any point, and when we talk about at any point, we're talking about displacement. The potential energy is equal to half m omega squared x squared. And we know that the total energy is half m omega squared a squared. We said that the total energy is given by the kinetic energy and the potential energy. So at the equilibrium point, the total energy is directly from the kinetic energy. And at the amplitude, the total energy is given by the potential energy. So we know how to find maximum kinetic energy and maximum potential energies. Okay? We've talked about velocity at any point is given as v equals to omega the square root of a squared minus x squared. Okay, so for questions and answers, kindly watch the upcoming videos, and do not forget to subscribe, like, and share, and also hit on the notification bell so that whenever a new video comes, you can be aware of it. Thank you.